Hello, Flat Earth researchers, debaters, and especially debunkers. Very briefly, think about that famous experiment where they drop a feather and a hammer in a vacuum, and those two objects apparently falling to the ground at the same speed is proof of gravity, right? Well, actually, it completely disproves gravity. First of all, the experiment was taking out the air molecules, so the feather has no resistance against the air molecules. Fine, okay? Now, gravity is said to be an inverse square law, so that should naturally affect lighter objects much more readily than it affects heavy objects. As I've said before, like sucking up a feather in a vacuum cleaner is going to be a lot easier than sucking up something heavier, or a paperclip rushing to stick to a magnet compared to a heavy steel ball. Yeah? The magnet is going to attract the paperclip much more quickly and easily and make that paperclip stick than it will the steel ball. Yeah? So, one of two things should happen if gravity were real when you drop a feather and a hammer in a vacuum. One, the feather rushes to the ground faster than the hammer because it is being more quickly and more readily affected by gravity. Or, the same thing happens as normal with the feather. It floats and the hammer hits the ground first. Why? Because the usual excuse for gravity is that everything has its own mass and has its own center of gravity. So, in that respect, the feather, being very lightweight, having hardly any mass, should just float gently down to the ground, even in a vacuum. And the hammer should hit the ground before the feather, as normal. The only reason that the hammer and the feather fall at the same time to the ground in a vacuum is because you took the air out.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Dropping the hammer and the feather, and sure enough they both fall together, and that proves immediately that this experiment was done in a vacuum. So this movie set would have to have been evacuated. It would have to be a vacuum. But more than that, the two objects fall slowly. They would fall 6 times faster on the Earth because the gravity is stronger. You see them fall slowly on the moon.
And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
This is also a very difficult image to fake.
Well, actually, it isn't at all difficult to fake. NASA itself would repeat the very same trick, this time officially in the 1999 story From the Earth to the Moon. This time the astronaut held the hammer the other way up, so that we could see it was not the same fakery as the first time. Of course, that original demonstration by Apollo 15 doesn't in any way prove that it had taken place on the moon. Before NASA reenacted the whole thing officially, we had already conducted our own experiment. Here we are in our London studio in 1G, complete with an atmosphere, and without the benefit of a vacuum chamber. There they go. As you can see, the feather and the hammer arrive on the ground at the same time. Now if we slow it down by the appropriate amount, lo and behold, these two items fall nice and slowly as per a 1/6 G environment. This illusion is all about calibration.
Thanks again for joining me on my mental journey to discover the truth about our amazing home, Earth. I'm titling this video, Gravity is Not What We Think. What Are They Hiding? In this video, I'm sharing my deeper look at the popular video starring Brian Cox where he visits NASA's biggest vacuum chamber to allegedly demonstrate how gravity works in an environment free of air. The first thing that caught my eye when I watched this video was the editing out of a feather falling before its time. I'm not sure why they felt the need to cut that out. It didn't seem like a big deal to me. It just seemed like they just could have kept the cameras rolling and went with it. But giving them the benefit of the doubt, let's just say they wanted everything to be perfect just because. But I'm already getting a sense that this video is not straightforward. The first drop seems legit at first blush, but it's actually all chopped up. And this is the only sequence that includes the actual dropping of multiple feathers and where the lighting is actually good. Later, the multiple feather drop is gone and all the overhead lights are turned off. I wonder how many hours of shooting they had to do to make this 4-minute video, or even this 4-second clip. This is exactly what you get after the drop in the first example. First, the feathers falling in all directions, then the feathers falling back in a cluster, then that cluster magically landing in the right spot, and then the feathers are gone altogether. And all this in 4 seconds. Seems legit, right? The second example of a non-vacuum fall has several lights turned off and starts with a drop of a single feather and ball, and then the ball landing without any feathers in the shot, and then we see multiple feathers falling together to imply they haven't even come close to landing yet. But then that's all we see. We don't see the feathers landing, and we never see this whole thing without any cuts. Obviously the cut job is bad because it starts with 1 feather and ends with at least 3 feathers. If there was no deception here, why not show the whole sequence straight up, from release to landing? Do they really expect us to believe that these 3 cuts are all from a single event? Obviously they are not. Now we'll be getting into their example that supposedly takes place in a vacuum. On this slide, I added a snapshot of both the alleged non-vacuum on top and the vacuum on bottom footage in order to get a side-by-side view. Notice anything fishy? To me, the vacuum footage is more grayed out and the focus isn't as good. In this non-vacuum clip in the video, you don't see the actual release and you never see the bottom of the feather. The feather to me doesn't seem to be behaving right either. Is gravity getting a little help? I don't know. Can't see. Anyway, I had a theory that the ball was edited into the feather footage later. And sure enough, when I made a few adjustments to the image in Photoshop, an apparent pixel border revealed itself. But that's not all. This video continues to insult our intelligence completely. Do they actually expect us to believe these 2 clips represent a single uniform event? They try anyway. See for yourself. How do we go from 1 feather to a group of feathers? Unless the magic of gravity has the ability to add feathers. Just like the non-vacuum footage, you never see any uncut vacuum test footage either. It's always these 3 clips you see here. You start with 1 feather, as we discussed, then it cuts to some blurry long-range shot of the feather cluster and the ball group falling together, and then they cut again to the landing perfectly on the box. If they want close-ups and whatnot, that's fine, but at least 1 real-time continuous shot of the whole event from beginning to end should have been included. What do they've got to hide, right? And I'm not in a vacuum expert, but the feathers not tipping at least a little bit due to their variance and weight balance seems very odd to me. And don't things expand in a vacuum too? Just saying. I noticed as I watched the blurry, overexposed, long-range shot that the background around the falling bundle seemed to be getting smudgy, and you can see that for yourself. I thought this could use a Photoshop test. With just a few minor adjustments, I got this image here. It looks to me like a cut and paste job. You can try this yourself and see what you think. Just try adjusting shadows or reducing contrast, and then bring up the color saturation all the way and see what you get. This shot here is the very last frame you'll get to see in this not at all straightforward and badly cropped footage. They totally leave us hanging. They never show the final landing after the bounce. Was there more than one bounce? Does the ball land in the same spot? Do the feathers stay afloat? Do the feathers drop fast again? I mean, come on! Okay, now I need to pick on all the drama from the video. I can't leave it out completely because it does constitute half of the 4-minute video after all. Is it just me, or are Brian and the NASA guy playing it up too much? Look at the guy at the terminal. He's like, oh, that's right, I'm supposed to be excited. Even if it wasn't all garbage, his reaction is at least more of what I would expect. A simple smile and a nod of approval is all you really need here. Or maybe this reaction shot was done while these guys were looking at the actual uncut and unedited footage, where cooler things might be happening, like feathers beating the ball to the ground, or feathers exploding. You might be thinking, okay, Fran, this experiment has been done by others. Well, of course I had to check out the other footage. It wouldn't be fair to just examine the most popular and publicized video. The reason I said that maybe our actor crew was watching the feathers beat the ball to the ground was because that's exactly what I saw over and over again when I slowed down the other videos of this type of experiment. The other videos varied a lot in their presentation style, and some used tubes while others used a chamber. But in all the videos, lighter objects stay ahead of the heavier ones. This particular video was tricky to slow down because it all happens in the blink of an eye, but the feather clearly beats the ball. Again, the feather is actually ahead of the ball when you slow it down and pause. The image quality of this video isn't very good, but you can see that the feather is beating the ball on the first part of it where the whole apparatus is shown, but it's very blurry. So I didn't use that, though I didn't use those images. And I don't know why this bothers me so much, but I noticed the operator always keeps the tubes to a tilt for some reason. And in my humble opinion, these experiments fall short of proving much. The only thing they prove to me is that without air, feathers fall fast. But did we expect anything different? Air resistance is exactly what feathers are designed to do, after all. In this video, the tube is flipped twice, if I remember right, and one of those times the hammer object was actually on top of the poor feather. Sometimes I wonder if these vacuumed tubes get some kind of electrical static to them during this process. Are these tubes and parts all made from some special plastic that prevents it from collecting charge? Feathers love to stick to balloons, you know. Come on, Brainiacs, help me out here. And this is my second favorite video, before we get to the next one, which is my first favorite. But this one's my second favorite because both objects are about the same size and shape, and because it is more clear than some of the other videos. In this video, again, it seems like they are the same when viewed at regular speed, but they are not. The lighter object is ahead. In this particular video, I like that they've added a third element. None of the others I saw did this. Therefore, this is a better experiment in my book. The clarity of this video is pretty good too. However, we are only provided one example of each before and after. I would have liked to see it done repeatedly with the same objects and then done again with different objects. Even in this video, the feather is now ahead of the heavier ball in vacuum. It seems from my observations of all these videos that a vacuum chamber changes the game to such a degree that feathers actually beat their heavier companions with consistency. I don't understand why this is not addressed. Surely I'm not the only one noticing this, right? I know people often just see what they want to see, but come on people, take a deeper look. It's right there if you just pause the videos. I think the implications are amazing, but what I need are the Brainiacs to wake up. Obviously, I think that the popular video is completely dishonest, but I find the other videos to be too much taken for granted. Most don't have good quality video, and most only use two objects, and none use a variety of objects, and none discuss the other scientific stuff that might be taking place, such as a shift in pressure within the vacuum, or a change in static charge due to vacuuming. Have you ever seen the peeps in a vacuum experiment? If not, check it out and ask yourself, does going from air pressure to no air pressure and then back to air pressure have an effect on the structure of other objects as well? It would seem that feathers would probably expand to some max fluffiness, right? Just more to think about when you watch these videos for yourself. Thank you for watching, and I hope you got something from it. I also hope you will ponder the questions I've raised. I will be back with more presentations in order to continue sharing my mental journey to discover the truth about our amazing home, Earth.
So we heard it again and again. Objects with the same mass falls with the same speed. If I drop a 1 kilogram bowling ball, it will hit the ground at the same time as a 2 kilogram bowling ball. Or if I drop a hammer and a feather in vacuum, they will hit the ground at the same time.
How about that? This proves that Mr. Galileo was correct in his findings.
So do objects fall in the same speed no matter their mass? Well, actually, not quite. You can argue that heavier objects actually fall faster than lighter objects. The collision time is faster. So what's going on? Well, do you remember this equation? This is the force of gravity between two objects of mass 1 and mass 2. It's just their masses times the gravitational constant over the distance squared.
So if we drop the hammer, let's see what happens. First, we are looking at the force on the hammer, so let's switch the index to hammer. Next, pretend we are dropping the hammer just a little bit above the radius of the Earth. Let's insert the radius of the Earth. We have the mass of the Earth and the mass of the hammer. According to Newton's second law, the force on the hammer is the acceleration on the hammer times the mass of the hammer. So let's insert that. So we can see that the mass of the hammers cancels. Goodbye. And if you plug in the numbers, well, then we get 9.8 meters per second. That's the gravitational acceleration on Earth.
3, 2, 1. Before I do it, so there's no air in there now, and let's see if you're correct. So your prediction: 3, 2, 1.
Pretty confident that we'll get at least a decent result, if not a perfect result. 3, 2, 1. Feather plummeting like a brick. Oh, it was great.
It didn't even move.
appreciate how fast the feather actually falls. So here's feather in a vacuum, normal speed. 3, 2, 1. And appreciate how fast the feather actually falls. So here's feather in a vacuum, normal speed. 3, 2, 1.
There you go. So I hope you predicted it correct. As you can see, they both hit the ground at the same time.
So as you can see.
So I hope you predicted it correct. As you can see, they both hit the ground at the same time. They both hit the ground at the same time.
Feather plummeting like a brick. Oh, great!
So as you can see, they both hit the ground at the same time.
Hey guys, Will here, and I want to talk today about gravity, and this title of this video is absolutely perfect. The misconceptions about falling objects. So let's watch this real quick.
At exactly the same time, what do you expect to see?
Well, they're going to hit the ground at the same time. I expect them to both land at the same time.
Same time.
Same time.
Well, I think they both will. This one to hit the ground.
One clearly greater rate and reach the ground first.
So the thing is here, he's got a heavier ball and a lighter ball.
The balls are speeding up as they go towards the ground. That's what the force of gravity does on them. It makes them accelerate. It gets them to speed up. Another misconception I discovered was that some people believe both balls should have the same gravitational force on them, even though the black ball is clearly much, much heavier. The reason I think they said this was because they knew both balls needed to reach the ground at the same time, so they reasoned that the force on them must be the same. Tell me about how the gravitational force on this ball compares to the gravitational force on that ball.
The force is the same.
It's going to be very similar. In terms of gravitational pull, they're both at the same, and they'll fall at the same rate.
I don't know like Einstein, but same gravitational force around the whole world, right?
Because the gravitational pull on the Earth.
Okay, here, he's gonna drop it here.
In real life?
In real life and in physics, I will tell you that the force on this ball is more. All right, ready? 3, 2, 1.
Yep, see? Same time.
I would say the force on the medicine ball is like a lot more.
Okay, guys, if you saw there, he was dropping the balls from just above his head, and thinking that's a scientific experiment, you know, that this proves it. And oh, look, they hit at the same time. Now, is this a way to test science? No, it's not. So let's see if we can find out a little bit more about this, right? Let's look which hits the ground first.
I'm Manoj Bhargav, the founder of 5 Hour Energy.
This is a very...
Now I'd like you to make a prediction.
Same guy. Yeah, I didn't mean to... But, yeah, which hits the ground first, and he's doing the same thing, right? He's basically holding it above his head and looking at that. So, this is quite a question for the flat earth, because gravity's based, or the theory of gravity, the hypothesis of gravity is based on a round earth model where the gravity is centered towards the core. A friend of mine was talking yesterday, and so that's gravity's towards the core, that's towards the center, so he was kind of making the analogy that then gravity would be towards the North Pole because it's towards the center. But you know, I personally think that's a complete misconception. So he was kind of taking a clue from these guys, or from this type of experiment, and it was his assertion that, hey, if you drop a hammer and a tennis ball, they're going to fall at the same speed, they're going to hit at the same time. And I said, no, they won't. That's not physics. They will only fall at the same time in a vacuum. So it was really quite, you know, my understanding of physics, it was really quite different to see this, see these misconceptions, because it didn't seem to line up with what I had been taught in school, or what I had known, or my understanding of such. So I sought out to either correct myself or to find out a little bit more about this. And I found this video. Let's watch this video. I thought it was pretty darn accurate. Pretty good tests.
Agree on one of history's most and this is a cooker. Both household objects, but both used for very different purposes, as I know from bitter experience. The cooker weighs 400 times more than the pillow. John, what do you think's going to happen?
Well, Aristotle will say that the cooker is going to fall 400 times as fast as the pillow, whereas Galileo will maintain that they'll hit the ground at the same time. I'm with Galileo. The mass of the object has absolutely nothing to do with the speed with which it will fall.
I think the cooker's going to land first, and the pillow will float down gently. Let's find out. Come on, let's go and find out.
This is science. They're going to fall exactly the same way.
Myth has it that in Renaissance Italy, Galileo proved that light and heavy objects fall at the same speed by dropping 2 cannonballs of different weights from the Leaning Tower of Pisa. Meanwhile, in ancient Greece, Aristotle thought light and heavy objects fall at very different speeds. But being a typical philosopher, he never bothered testing anything in the real world. So it falls to us to winch a cooker and a pillow up to a height of 60 meters and finally answer the question. Right there.
We'll see who's right now, Vic.
I think you'll find that it's me. That goggle's on.
Right, yeah.
Let it drop!
The question we reach at this point is heavier object versus lighter object. So how will they hit differently? Will they hit differently? And what will the causes be? Will the causes simply be air resistance? I mean, these are not the same shape, but will the air be able to... Okay, so you have to think of a feather and a tennis ball. So, okay, the feather falls a lot slower because of air resistance. But if those two things are the same shape, the air resistance is less of a issue, is then more density and mass. So let's see what happens here.
Let it drop!
Oh, there they go, there they go! No!
pillow still floats.
Oh, that's taking ages.
I think I won that round there.
So as you saw there, the pillow floated down. Just did not have the acceleration. Sure, that's likely from air resistance. I agree. But let's look at their next test.
The cooker goes off like a hare, whilst the tortoise-like pillow follows leisurely in its wake. Only a fool would say that Aristotle wasn't completely right.
Aristotle wasn't completely right, was he? Because if he was right, this would have fallen 400...
The same height as the Leaning Tower of Pisa. Well, it's 1-0 to Aristotle, but now we're on Galileo's home ground with two...
And here's this next accurate test. Two balls nearly identical in size and vastly different weights. So one can assume that air resistance should not play a difference in this experiment. Let's continue.
Balls of dramatically different weights. We've got a cannonball and the football. What's going to happen, John?
Well, Vic, I've been having a think, and I reckon the lack of aerodynamic properties of the pillow combined with its relatively low mass meant it was more susceptible to air resistance. Now, as you pointed out, vastly different masses on these balls, but the same aerodynamic shape, so air resistance shouldn't be a factor.
So which one's going to hit the ground first?
It's going to fall at the same rate and hit the ground at the same time.
I think you'll find it's the cannonball.
No,
Let's find out.
I'm going to prove you wrong.
For the first time in 400 years, two balls of different weight dropped from the height of the world's most famous wonky bell tower.
I have absolute faith in our friend Galileo.
What, an iron cannonball?
Yeah, and a brass cannonball.
But that's a football filled with air.
It doesn't matter, they're the same shape, so they're going to hit the ground at exactly the same time, I reckon.
Let it drop!
Now, it's important to consider that we must think of the experiment with the guy holding the balls above his head and dropping at a distance of what, 6 feet, 6.5 feet. Is it going to be a measurable distance at that? Is the difference going to be measurable at that distance? And if you look, the falling is almost the same. There is a slight difference in the beginning. So you wouldn't have really seen much of the difference, but then the difference becomes apparent as they fall faster and as the cannonball speeds up quicker. So it is absolutely apparent that the objects do not fall the same. I'm not saying that this disproved gravity or proves gravity or anything like that, but that there is misconceptions about gravity, and you know, even if you hear this guy trying to rationalize, let's listen to him trying to rationalize how they came different.
First. Well, technically the cannonball. Got a theory.
Technically it did.
I've got a theory about it though.
Yeah?
Light objects like the football will only accelerate for a certain amount of time until air resistance counteracts the acceleration due to gravity. And it'll reach its steady speed known as the terminal velocity. With a heavy object like the cannonball, air resistance isn't such a factor. It won't reach its terminal velocity.
So what do we do about that?
We'd like to have the experiment in an airless vacuum and then air resistance wouldn't be a factor.
Well, we couldn't arrange for an airless vacuum in our car park. Instead, we've got...
Okay, so I understand that these two are just playing their roles and that one needs to be a dissenter.
Galileo proved that light and heavy objects...
you know, they need to be on the different sides. But the way at which this guy tries to explain away the differences that are apparent in an experiment is the way that people try to rationalize things that are beyond rationalization. I'm not saying they're beyond rationalization, but they're beyond they're beyond their comprehension. So they try to make up these scientific reasons for why they are wrong. I'm not sure that I believe in gravity. I've read the debates that, it's actually just density and mass. And that's all, that everything in the world is density and mass, which is quite interesting. So guys, I think there's reason to believe that there's misconceptions about gravity in our culture and even in our science, because don't forget, we looked at these guys trying to Veritasium. We looked at these guys trying to give these scientific academic opinions and even showing experiments, and they are wrong. So, is it possible that the basis on which these theories are founded, gravity, are wrong? So people talk about Sir Isaac Newton and how he developed gravity. Well, actually, he developed gravity as a hypothesis. He never said that gravity was real and that gravity was 100% for sure. That is, our modern science has said that with no proof. So guys, experiment for yourself, please. Research for yourself. Find the light for yourself, because in finding the light, you will find the lies. Thanks a lot. I love you guys. I'm just waiting for all this knowledge to get out there. The knowledge about the flat earth, the knowledge of the inefficiency of our scientific system, scientific theories and hypotheses that are listed as fact when they're only opinions. So it's just a little bit of the things that are making me more and more skeptical of mainstream science. Till another day, William